So imagine I start with this curve, y equals square root of x, and I work at a rocket factory and my boss wants me to make the nose cone of my rocket so that it has this shape. So I could do that. Might be your first time. So you have to imagine taking this shape, that shape under that sideways half a parabola, and revolving it around the x-axis to produce this solid figure. Now, since the region I was revolving is completely flush, let's see what I mean by that. Completely bumped up against the x-axis here. There's no space between this region and the x-axis. That means when I do that, the solid I make is actually going to be solid. There's no holes, no gaps. It's going to be a solid chunk of whatever I've made my rocket nose cone out of. So the next question we might like to ask is, how could I find the volume of that nose cone? So this is going to be this next important idea for us. If we form a solid shape by taking a region, a two-dimensional region, and revolving it around an axis, how can we then find the volume of the solid that results? So what we're going to do every single time, so we're going to pretend we're going to slice that shape into slices that look like really thin cylinders, which we call discs, which is why this method is going to get its name, the disc method. So that looks like a quarter. So a really, really, really flat cylinder, a disc. And hopefully this is bringing up happy memories of what the project you just did, where you've taken your bucket and you've sliced it into really thin cylinders and added up the volumes of all those cylinders. So we have that same kind of thing going here. It's just now our bucket is on the side and we're taking our slices vertically. Okay, so imagine we cut this shape up into cylinders. The volume of each cylinder, this is the part that you practice lots and lots, is going to be pi times r squared times the thickness of the cylinder. In this case, the radius is that distance, which is the distance between the x-axis, y equals 0, and this curve, y equals square root of x. So more on this and how to draw it and how to pick your radius in a second. But just notice, if we know that that's a formula for the radius, then we have pi r squared thickness, and we can just add up all these volumes by integrating. So you can see there the r is the y value of our function, this sideways parabola, and the thickness of each cylinder is a small change in x, so dx. If we add up those volumes of those infinitely many, infinitely thin discs, we're integrating over the total x distance covered by our nose cone, which is the distance from 0 to 4. This expression we can simplify because the radical x can get squared, and you have something really similar to step 9 from your lab report there. We can evaluate our antiderivative is pi over 2 x squared, and then evaluate from 0 to 4, and we get 8 pi as our volume. So go back to these steps, which are printed in your notes. So my experience so far teaching calculus is that once you decide that you're going to revolve a two-dimensional area around an axis, there's really only two decisions left to make when we're going to write an integral to find the volume of that solid. Number one, is there going to be a hole in the middle of the solid? So far we haven't seen one because our region that we're revolving bumps up all the way against the axis that we're revolving around. And then the second question is, well, what's the radius? If we're always going to use pi r squared, because we're always going to cut into cylinders which have volume pi r squared times the thickness, the only thing left to do is figure out the radius. So I'm going to suggest that you use these steps every time to sort of help you focus in on how to figure out what your radius is for the disc, the infinite number of discs that you're going to be adding up. So here's what I'm going to suggest if you had to do that nose cone problem on your own. My first suggestion is that you make it very clear what region is going to get revolved, and then come through and do something to sort of lightly shade that region so it's clear what's getting revolved. My next recommendation is that you figure out what the axis of revolution is. In this problem, they weren't very specific about it, but you'll find that on AP tests, they're very specific about the line that you're going to revolve around. So here we were revolving around the x-axis. I'm going to take the x-axis, I'm going to color it in red. Now what I want to do to help me sort of visualize the revolving that happens, I'm going to take that shaded region and I'm going to try to reflect it around the axis of revolution. So I'm going to color that in. I'm not going to shade that part. If you want to be a little bit silly about it, you could show that that's R reflected. That's not a big deal. And your picture doesn't have to be perfect. Nobody's going to judge you on how parabola-y your reflection is. We just want to sort of get an idea of the shape, because we're going to have to model the volume of this shape with an integral. So let's read this next part before I do it. We're going to try to draw in what one slice would look like. It's going to look like a flat cylinder, so a disc. And my recommendation is that you start your green pen, your green marker, on the axis of revolution. You're going to draw up toward the far edge of the shaded region, then back down, pretending you're coming back down behind the axis of revolution, down to the far edge of the reflected region, and coming back up to the axis of revolution. So, does that look like a really awesome circular slice? Not really, but you can see how that compares to the green slice that was in the PowerPoint at the beginning. That's going to help us model what's happening here. So I copied my green disc over there just to kind of help us see what it is. Now, the tricky part is going to be able to figure out what the radius of that green disc is. So let's just sort of make a plan for how we're going to find that. My recommendation is that you try to draw in the radius of the green disc by starting your pen, your blue, at the red axis of revolution and draw toward the far edge of the shaded region. So over here, just to sort of show you that process, I was starting at the middle, the center of the disc, right? I'm going to draw toward the edge of the shaded region. So I drew up because the up is where the shading is. I'm going to do this in red. No, I'll do it in orange so you don't do it. I didn't draw down, not because that's not the radius, but because that's not into the shaded region. It's going to help you if you do draw your radius toward the shaded region. Okay. Do that one. So now, can I think of a way, sort of an algebra way to describe the length of that blue radius I drew in? Well, no matter where I take my green slice, the top of the blue radius is going to be y equals square root of x. The bottom of the blue radius is always that axis of revolution, which was y equals 0. It's a vertical line for the radius, and the way you find the distance along a vertical line is to subtract the y values. So I would subtract top minus bottom, that's radical x minus 0. So I would say that my radius is always square root of x minus 0, or just square root of x. Now that I have an expression for the radius, it's easy to write my integral. This is going to be pi radius squared. My green discs here, I can see, I hope you can see, it's fairly easy if you look back at the picture from the PowerPoint, but you can see that that green disc is sort of turned so that its thickness is a very small change in x. That tells me I'm integrating with respect to x. Here, my r goes in the parentheses. My r was radical x. Inside my integral, all I have is x's, which means the limits have to be x limits. So this is going to be 0 to 4. One more thing just to mention, it's written on in your steps, but you should be absolutely 100% certain that your slice is perpendicular to the axis of revolution. So that's your process for writing an integral for the volume of a solid that you produce by revolving a region around an axis.